In this video, you'll learn everything that you need to know about the DFS pattern or depth first search pattern so that you can start applying it to common problems. The DFS pattern can be applied to many different problems, so it is, in my opinion, one of the most useful patterns to understand. There are some pitfalls though, so make sure you stick around until the end of the video to gain a complete understanding of how to avoid the common misconceptions. So to start, you should keep in mind that I'm going to be referring to trees and graphs as if they are different things, when in reality, a tree is just a type of graph. But this is just because the algorithm will differ slightly when dealing with graphs that are trees as opposed to graphs that aren't trees, and vice versa. So let's start with what makes a graph a tree. A connected acyclic graph is called a tree, and acyclic is just a fancy way of saying that the graph contains no cycles. And connected graph is just a fancy way of saying that every node in the graph can reach any other node in the graph, or every node has a path to any other node in the graph. So that means that the visualization that you're seeing now will work with the starting node being any of the nodes in the tree if the graph is a connected graph. So there are three traversal orders that we need to consider in regard to DFS on a tree, or DFS on a connected graph with no cycles. Those are in order, pre-order, and post-order. To understand these traversal orders, let's take a tree into consideration. If we want to search for the letter A in this tree, we can use DFS in either one of the before mentioned orders. So let's go with in order traversal. In order traversal simply means that we search each subtree in the order left, root, then right. So let's go ahead and emphasize the subtrees here. So here we have a subtree, here we have another subtree, and here we have one more subtree. We start at the root of the whole tree, which is also the root of this subtree, and then we will first search the left node of this subtree, which is also the root node of this subtree. So in a depth first manner, we must search this subtree before moving on to the next node of our top level subtree. Next, we search the left of this subtree. The left of this subtree is a leaf node, which is just a node that doesn't have any children, so we've reached the maximum depth here. And this node doesn't contain our value, so we now can search the next node, which is the root node, when doing in order traversal. So the root of this tree is here, so we can check this node. It doesn't contain our value either, so now we check this subtree's right node. That node also doesn't contain our value, so we move back up to the previous subtree. We left off at this subtree's left node, which we already checked, so now we move to this subtree's root node. This node doesn't contain our value, so we move to this subtree's right node. This right node is the root node of this subtree, so we start by checking this subtree's left node. That doesn't contain our value, so we move to this subtree's root node. This node doesn't contain our value, so we move to this subtree's right node. And this right node does contain our value, so we have found our value and can finish. And that is how DFS works when doing in order traversal. The other traversal orders, pre-order and post-order, work in the same way. The only difference is the order in which you check nodes in each individual subtree. But regardless of the order, the search happens in a depth first manner, hence depth first search. So now that we've gotten traversal order out of the way, we need to understand the difference between DFS on a tree, or a graph that is a tree, and DFS on a graph. So the previous example was DFS on a tree. The most important thing to understand about DFS on a tree versus DFS on a graph is that trees do not have cycles, but graphs can have cycles. And as mentioned before, this is what a cycle looks like on a graph. A cycle is just a path that starts from one node and ends at that same node. As you can see here, our starting node is the same as our ending node. So what does that mean for our algorithm? Well, now we need to take into consideration the possibility of visiting a node twice. With the tree, it wasn't possible to visit the same node twice because a tree contains no cycles. So the algorithm for DFS on a tree is a tiny bit simpler, but don't worry, the algorithm doesn't change much for DFS on a graph. We just need to keep track of nodes that we've already visited. So let's take a cyclic graph into consideration. And a cyclic graph is simply a graph that contains one or more cycles. So we'll start at this node here, and as we visit the nodes, we'll mark them as visited by changing the color of the node to red. So when we get to this next node, there are two different directions that we can take. Which one we take doesn't matter because we haven't yet visited the nodes in either direction. So we can just pick one. And here we can only go in one direction. Same here, we can only go in one direction. Here, there are three directions that we can go, but one direction leads to an already visited node. So that one can be eliminated from the possibilities. Now we're left with two directions. Both lead to nodes that we haven't yet visited, so we can just pick one. Now, once we get to this node, the only direction that we can go leads to an already visited node. So that means that we now have to backtrack. We'll use orange to represent backtracking. Now we're back at the node where we had two possible paths. One path we have already visited, so now we're only left with the one path that we haven't yet visited. So once at this node, there's nowhere else for us to go. We've reached the depth. So all we can do is backtrack. Same here, nowhere else to go, so we backtrack. Same here, and same here. And remember, here we had a choice between two paths, but we chose the one that we just backtracked from. But as you can see, with the chosen path, we were already able to visit the node that the other path option led to. So that node is already visited, so we just backtrack here as well. And the same with this last node. The other potential path was already visited, so we just backtrack. And since this is the starting node, we just return out of the algorithm at this point. So as you can see, we went all the way down to the deepest possible depth of the graph before returning to the starting node and checking the other paths. And that is why this is a depth-first traversal. So let's go ahead and get into what I think makes this algorithm absolutely beautiful. So let's imagine that we have a group of graphs independent of one another, and we want to know how many of these independent graphs exist within a given grid. Some of you may have already noticed this is actually what is asked in a popular coding problem called number of islands. At first glance, this problem wouldn't strike you as a problem that can be solved with depth-first search or depth-first traversal. But when we insert the grid, you see that the so-called islands within the grid are actually just cyclic graphs. So we can iterate through the grid using a for loop nested within another for loop, and when we reach a node in the grid that represents a piece of an island, we can just use that node as the root and traverse the island using depth-first traversal to determine the size of the island within the grid, and also mark the island's nodes as visited so that we won't count them when counting other islands. So counting each individual island after we've traversed it will in the end give us the answer to the number of islands in the grid. And once you've gotten to the point where you can essentially visualize where DFS can be applied to other problems, I'm confident that you too will come to see the beauty in this algorithm. And that's going to be it for the depth-first search pattern. So if you found this video helpful, please take the time to leave a like, and I will see you in the next one.